Supposing that you could do an infinitely accurate calculation that absolutely mirrored what experiment found. And Tom will probably try and convince you this afternoon that that day has arrived, that one can do calculations that accurate. What would you have learned? What would you have learned beyond what you knew already from the experiment? I think that what one wants to do is to get a little bit deeper, and sometimes one can do that with calculations. In fact, working out mechanisms of organometallic reactions on computers has become a sort of cottage industry. I handle lots and lots of papers that do that these days. But still, one would like to have some more fundamental insight into what's going on when, for instance, in one reaction I'll talk about today, a reaction that's a reductive elimination first eliminates something. I mean, that seems pretty bizarre. Another reaction, it's an addition reaction, something adds first. And all one can do with a calculation is say, yeah, that's what happens. So what one would like to do is try and get some insight in some way or other into what's going on fundamentally. And I would claim that molecular orbital theory provides a very, very good way of doing that, particularly since the computational methodology that most people use is based on molecular orbital theory. So you can come up with a hypothesis and then look at more than just the energies and geometries. You can actually look at the orbitals that you've generated. And that's what I'm going to show you today is lots of orbitals. Okay? So I have two people to thank, first of all. Joe Feng Kei, who's in the audience, and David Rovat are responsible for all the graphics that you'll see today. I really thought that I wanted to show you not cartoons, but real molecular orbitals. And so they provided me with all the molecular orbitals you'll be seeing. And when I told Karen the topics I was going to cover, is Karen here so I can make fun of her without worrying about upsetting her? No, Karen isn't here. Okay, so when I told Karen what I was going to talk about, she sort of sounded like, oh, everybody knows that, right? Which worried me because, as you will see, my knowledge of organometallic chemistry is really, really limited. So I got a little worried, but I thought I would start slowly and kind of work you into. And so if you know all this stuff already, then you don't have to pay much attention. So here's where I thought I would start. If this isn't simple enough, then maybe we could start even simpler. So I'm really going to start from the beginning and go really slowly. And if you're bored, maybe later on, when we actually see that diagram, you'll appreciate the background. Okay, so supposing we have two hydrogen atoms. As you know, electrons are quantum mechanical objects. They're not waves, they're not particles, they're wavicles. And because of their wave-like properties, they interfere with each other. You can either take an in-phase combination of these two atomic orbitals and get constructive interference, or you can take an out-of-phase combination and get destructive interference. Clearly, this is the bonding combination. How do we know that? Well, we always draw a little line, between two atoms when they're bound, and clearly that has something to do with the electrons, and we'll come back to that. And we'll talk a little bit about what actually makes a chemical bond. In simple Huckel theory, the energy of these orbitals is supposed to be alpha, and beta is a parameter that tells you, how much bonding there is. So bonding orbital has energy alpha where you started, and beta for that much bonding. And the energy of the anti-bonding orbital is just at this level of approximation as anti-bonding as the bonding orbital is bonding. There are the actual orbitals drawn by or created by Dave Rovat. And I think what you can see is that the picture I had is not exactly right. You can see that when the orbitals interfere constructively, there actually is some region of space where the wave functions add. This is called the overlap region. And in this orbital, there's a region of space in which there's a node in which the electrons are not found. And as a result, what one really should do is renormalize one's wave function to account for the fact that we're not creating or destroying electron density here. We have to renormalize to account for the fact that we have an extra contribution from this overlap region. That's the S. So we have to divide what was the energy, alpha plus beta, over 1 plus S. And we also have to renormalize over here because we've destroyed some electron density here. And so we're going to wind up with an alpha minus beta over 1 minus S. Okay? And the main point is that since you're dividing this by 1 plus S and you're dividing this by 1 minus S, when you include overlap, that's S, bonding orbitals are not as bonding as antibonding orbitals are antibonding. Okay? In other words, if without S, this number was the same as that number, when you include S, you're dividing this by a number bigger than 1, you're dividing this by a number less than 1. Consequently, this goes up by more than this goes down. If we think for a moment about what we actually want to do, having created the molecular orbitals, we will start putting electrons in them, and that's sort of the scheme for the day, is create molecular orbitals and then fill them with electrons and see what we predict. And clearly we predict that if you have just one electron to make H2+, that you will get a bond, because we have one electron in this bonding orbital. And even better, if we put 2 electrons in, we get a stronger bond. What causes the bonding? Clearly it has something to do with this overlap region. And usually what people are told is that it has to do with the fact that if electrons sit in this overlap region, they're simultaneously attracted by both nuclei. How many people have heard that? How many people believe it? No one believes it. Some people believe it. Okay. Let me convince you that that has to be wrong. Okay? It has to be wrong, first of all, because if you do the math, you discover that, in fact, this is not a good place to be. It's sort of a saddle point. It's a high energy point. If you go along this line, it's a high energy point between these two, because Coulombic attraction goes as 1 over R. And clearly the best place for an electron to be is close to the nucleus, not in the middle here. So it is not electrostatics that creates chemical bonding. It's quantum mechanics. Without quantum mechanics, chemical bonds wouldn't exist. And most of you have had enough quantum mechanics to know about the particle in the box. So here are hydrogens represented as particles in boxes. The electrons are in little boxes. And maybe you remember when you worked on the particle in a box that the bigger the box is, the lower the energy. Anyone remember that from elementary quantum mechanics? So I'm going to claim that the reason we get bonding here is we got a big box. And that really is right. Okay? Really what's happening is the kinetic energy of the electrons goes down as the size of the area or the space in which they are allowed to move expands by virtue of the fact that these two orbitals overlap, creating essentially a bigger box. All right? And you can see why this is bad. Essentially what's happening here is we still have 2 boxes. There's a node here. The electron can't be here. In fact, we've sort of squeezed it in that direction because here this was spherically symmetrical. Here we sort of cut part of it off. So these boxes have actually gotten smaller. And that's why the energy would be alpha minus beta. The energy goes up. Okay? We've already noted that with inclusion of overlap, this goes up more than this goes down. And so if we have, instead of H2, we have He2, so that we have a total of 4 electrons, 2 on each atom, to put into these orbitals. Then we fill up the bonding and the antibonding orbitals equally, and the result is not non-bonding, it's rather antibonding. So if you try and push 2 helium atoms together, they really don't want to go together, okay? Because essentially you can think of it as 2 electrons being here, 2 electrons being here, this being higher in energy than that, and so the harder you squeeze, the bigger S gets, the worse you are. And that's really what's responsible for van der Waals repulsions between molecules, is this fact that overlap between filled orbitals is a bad thing. You can show this mathematically. You can add the energy of the bonding orbital with 2 electrons and the energy of the antibonding orbital with 2 electrons, and then subtract the beginning energy, which is 4 alpha, and if you do the math, that number is positive, okay? So when we have orbitals that are equally filled, bonding and antibonding orbitals that are equally filled, net result is antibonding. Please remember that because you're going to use it in a second. And pretty soon I'm going to start asking you questions. So that's maybe the first lesson for today. So that number is bigger than 0. So the important conclusion is that equal occupancy of bonding and antibonding MOs results in net antibonding. How about Ag2+? Well, for Ag2+, we have 2 electrons on one helium and 1 on the other, and so we can put 2 electrons in the bonding orbital, only 1 in the antibonding orbital, and if you go through the math, you get some bonding. Not as strong as having just 1 electron here and no electrons here, because, again, having 1 electron here more than cancels the electron down here. But nevertheless, Ag2+ does exist. It's a real molecule, and I suppose in a way it's kind of impressive that, simple theory gets that right, because if you, told somebody, He2 doesn't exist, what do you think about Ag2+? They'd say, well, that sounds even worse than Ag2, so, surely that doesn't exist. But clearly, we are predicting that it does. So another important conclusion is that when you have more electrons in bonding than in antibonding orbitals, almost always you get net bonding. And this is an example. If you've done hydrogen, H2, you've also done ethylene. The only difference is that instead of having 1s orbitals overlapping, you have 2p orbitals overlapping, thanks to Dave Rovat. And so, of course, ethylene exists. If we add 1 more electron, so that we have 2 electrons here and 1 electron here, 2 in the bonding, 1 in the antibonding, we have something that we could think of as being hydrazine radical cation. Hydrazine radical cation is a stabilized species. There is a rather famous chemist at Wisconsin who made his living for many, many years doing hydrazine radical cations. So they certainly do exist. However, if you put 1 more electron in to make neutral hydrazine, that's bad. That's really bad. Okay? Now, normally, hydrazine escapes that real badness by, first of all, adopting a staggered conformation, and second, being pyramidal. But if you make the nitrogens in hydrazine planar so that you have a situation where you really do have what I've drawn here, then there is a huge barrier to passing the nitrogens past each other. Anybody know who discovered this? You'd be really surprised. Jean-Marie Lehn. Before Jean-Marie Lehn started doing cryptans and cavitans and all sorts of things, he actually was doing physical organic chemistry and looking at barriers in hydrazine derivatives with a amide attached to the hydrazine so that the nitrogen was planar, and he was finding barriers of like 20 kilocalories per mole to rotate these things past each other. How about if we have 2 pairs of AOs? Well, this could in fact be, for instance, N2. So far, no surprise. You get 2 double bonds and 2 pi bonds in N2 plus a single bond. That gives you the triple bond that we usually draw. And now we come to something that gives most undergraduates a very hard time. Supposing that we want to draw O2. Ask any undergraduate and they will produce that drawing. And they'll say that's what O2 is, because, gee, it satisfies the octet rule. They've done everything you asked. What's wrong with that? Is that oxygen? Is that the oxygen you're breathing? If it was the oxygen you're breathing, you wouldn't have your lungs very long. It's singlet oxygen, highly, highly reactive state of oxygen. The lowest state is a triplet. And one of the great successes of molecular orbital theory is the ability to predict this unequivocally. If oxygen didn't turn out to be a triplet, MO theory would be worthless, because here is a place where you can make a prediction. You can say, if the theory is worth anything, it must be a triplet. Why is that? I think most of you know. Why is it that this must be a triplet? Somebody's rule. Hund's rule, yeah. Hund's rule says if you have two degenerate orbitals and you put two electrons in them, you should put them in different orbitals with their spins parallel. Okay. We can see why you wouldn't want to put them in the same orbital, because they would repel each other coulombically, and that would be a bad thing. Why put them in different orbitals with their spins parallel rather than anti-parallel? Anyone know the answer to that one? Yeah, that's the mathematical way of saying it. Yes, there's an exchange integral that says this is good. That's absolutely right. Can somebody give a physical interpretation? Well, let me tell you what the physical interpretation is. If you have two electrons of the same spin, you all know something about what they can do. Can they be in the same orbital at the same time? No. Who says so? Pauli exclusion principle. There is a stronger statement of the Pauli exclusion principle that says not only can two electrons with parallel spins not be in the same orbital at the same time, they can't be in the same region of space at the same time. So that can never happen. This can happen if you have anti-parallel spins. Pauli principle says nothing about electrons of opposite spin. Electrons of the same spin cannot be in the same region of space at the same time. So the motions of those two electrons are correlated. They're going to avoid each other. And because they're going to avoid each other, they're going to have lower coulombic repulsion than if they had their spins paired. And that's why there is a negative J. It represents that fact, that the classical distribution of charge from which you would compute the energy actually has to be corrected by a K, because electrons of the same spin don't move independently. They correlate their motion to stay away from each other, because that's impossible. Okay? So you now know why the Pauli exclusion principle, why Hund's rule works, and you know something more about the Pauli exclusion principle than hopefully you did when you came in the door. Here's something for you to think about. Anyone know what the bond dissociation energy of N2 is? It's a big number. It's about 240 kilocalories per mole. Anyone know what the bond dissociation energy of O2 is? It's 120, that's right. Isn't that interesting? If you go from a nitrogen single bond to a double bond to a triple bond, you get 80 each time, and you get up to 240. But you put two more electrons in, and you lose half of your bonding. Why is that? Where are we putting the electrons? Antibonding orbitals. And what can you tell me about antibonding orbitals? There are more antibonding than bonding orbitals are bonding, right? There's another manifestation of that fact that more of you are familiar with. Not many people know what the O2 and N2 bond dissociation energies are off the top of their head. Tell me about F2. What do you know about the bond in F2? Very weak, 37 kilocalories per mole, right? And that's a surprise, because everyone says, well, fluorine forms really strong bonds. Why doesn't it form strong bonds to itself? My guess is it probably does form a very strong sigma bond to itself. But we're filling up anti-bonding pi orbitals. So when you see these lone pairs on fluorine, they're not innocuous. They are going half of them into bonding orbitals, half of them into anti-bonding orbitals, but the net result is anti-bonding, and presumably that's the reason why the F2 bond is so weak. So you sort of see where we're going with this. We're trying to explain, simple facts qualitatively, and hopefully we'll get to more complicated facts as the lecture goes on. So this is just to remind you of why the bond in F2 is weak. Here is the diagram where we now go from 2 orbitals to 3 orbitals, and I'm going to make a triangle of hydrogens. Okay? And I'm going to do it by saying I'm going to take one hydrogen, say that hydrogen, and I'm going to allow it to interact with these other two hydrogens. Okay? And I'm starting off remembering that there's a bonding orbital in H2 and an anti-bonding orbital in H2. I'm forgetting about overlap for the moment, just because it makes the math a little easier. And what I would like to point out is that this hydrogen only interacts with this orbital. It does not interact with that orbital. And the reason is that this hydrogen has the wrong symmetry to interact with this orbital. The easiest way to see that is to say, look, if there's a bond here, there's an equal antibond here, there is no net interaction. But you don't have to really compute that. You can just look and say, look, this is antisymmetric with respect to this plane. The hydrogen's symmetric. Consequently, there will be no interaction between them. So symmetry is really useful in terms of figuring out what you don't have to work on. So you don't ever have to do this calculation. You just look at the orbitals and say, this will never interact with that, but it will certainly interact with that. And when two orbitals interact, just as we saw in H2, one combination goes up and the other combination goes down. So this just to remind you that only wave functions of the same symmetry mix. So this is unchanged. It doesn't mix with anything. Whereas this hydrogen and this H2 molecule do in fact mix, and there are two wave functions that are created. One is the in-phase combination, if you'd like the bonding combination, where this interacts in phase with this to lower the energy, if you'd like, of this orbital. And the other combination is where this orbital interacts with this hydrogen in an anti-bonding way to raise the energy of that orbital. Okay? And this is a good rule to remember. Whenever two orbitals mix, one combination goes down and the other goes up. If you don't include overlap, the changes are equal and opposite. If you do include overlap, then the anti-bonding one goes up higher than the bonding one goes down. Here are the actual orbitals for H3. And this is just to show you that in Huckel theory, the interaction that we get actually is beta. Okay, and here's the statement that I just made. One can actually justify this mathematically using something called second-order perturbation theory. It's a very useful thing to know about. It's really easy to use. The energy changes by the interaction energy of the two wave functions that are being mixed divided by the energy difference between them. And the way you can see that if one goes up, the other is going to go down, is that if EI, which is the starting energy of I, is higher than that of J, then I will go up. This will be a positive number. If it's lower, then this will go down. And so since I and J switch, depending on which orbital you're looking at, either the one that comes from in-phase mixing or out-of-phase mixing, the energy changes without overlap are equal and opposite. You also see, and this is maybe the most important thing, that the closer two orbitals are in energy, the bigger the effect of their interaction will be. In fact, you can see there's a problem if two orbitals have exactly the same energy, because this blows up, right? You get 0 in the denominator, and so you wind up with an infinity. So you don't use second-order perturbation theory when two orbitals are too close in energy. Actually, this is a situation where they are a little too close to use second-order perturbation theory and get a very accurate answer. And when you do the math, you discover that this change is equal to 2 beta, and that is not what you get when you do the calculation accurately, and that's because second-order perturbation theory is an approximation. It's like expanding something in a power series. Okay, you know how power series, you overshoot and then undershoot, and finally you converge. Well, that's what second-order perturbation theory does. There's a third order and a fourth order, which hopefully will get things righter. But there is a problem with perturbation theory in that quantitatively, if things are too close, it's going to break down. But qualitatively, it's just fine. It tells you when two things mix, one goes up, the other goes down, and the closer the energy is of these two things that are mixed, the bigger the change caused by their mixing. So here is H3 plus, just 2 electrons. And you can see that H3 plus should be a perfectly stable molecule. Right? Only filled bonding orbitals. And H3 plus is indeed a very stable molecule. If you ever take a mass spec, positive ion mass spec, if you look down at mass 3, you'll see a huge peak. H3 plus is always formed whenever it can form. It's a very, very stable molecule. If we put one more electron in, something interesting happens. Then we have to put an electron up in one of these 2 antibonding orbitals. So supposing we put the extra electron up in this antibonding orbital. So here we have a totally symmetrical distribution of electron density, but here we don't. Here we have a node, and I think what you can guess is that if you put an electron in this orbital, the molecule is going to distort. Right? Those 2 bond lengths are going to get longer. That one will actually get shorter. That's what's going to happen. This is going to get longer. Those 2 will get shorter. If you put the electron in the other orbital, just the opposite happens. Now, those 2 hydrogens want to move away from each other, and this will move in that direction. And actually, these are 2 phases of the same vibration, and they're called Jahn-Teller distortions. Whenever you have 2 degenerate orbitals, and you put 1 electron in one of them, or an odd number of electrons in them, 2 in one and 1 in the other, you wind up always getting a distortion of the geometry. Okay, and you can see why that's so. You simply cannot have a symmetrical geometry. For those of you who like math, the distortion is linear, which means there's a cusp. There's a singularity at a geometry where all the bond lengths are equal. And these singularities are called avoided crossings, and they turn out to be very interesting and very important in photochemistry. But for our purposes, all we need to know is that this molecule distorts. There is another distortion that's also possible, and that's one that looks like this. And you can see that totally breaks symmetry, and it allows those 2 orbitals to mix, and you wind up with distortions that instead of having, say, this is the unique atom, have that as the unique atom, or that is the unique atom. And you can describe any distortion in terms of a combination of that and that. So now you know a little something about Jahn-Teller effects. Chemically, what does this mean? Well, chemically, I think what it means is that if this molecule is going to tend to distort such that this bond is going to get really, really long, essentially we're saying there's not going to be a lot of bonding between the hydrogen atom and the hydrogen molecule. If, in fact, what happens here is that these 2 atoms move away from each other, the logical extreme of that would be that the hydrogen H3 molecule would be linear. And indeed, that is the preferred geometry of H3. But of course, it isn't the minimum. It's a transition state for exchange of hydrogen atom. So let's look at that. Let's look at H3, linear H3, and let's build up the molecular orbitals for linear H3. Okay? Now we don't have symmetry, right? Because we're going to have 3 of these in a row, and although when this hydrogen sat in the middle here, it didn't interact with this antibonding orbital. If it sits on the end, there's no symmetry involved, so that this will interact with this, it will also interact with that. So when these 2 orbitals interact, what's going to happen to the lower orbital? What's going to happen to its energy? It's going to go down. And the energy of this orbital is going to go up. When 2 orbitals mix, the lower one goes down. When 2 orbitals mix, the upper one goes up. This one doesn't change at all. Why is that? Well, it has 2 interactions, right? It's being pushed upward by this interaction. It is being pushed downward by that interaction. And apparently, those 2 effects cancel. And this is rather important because what it says is that when you try and figure out what happens to an orbital that it is interacting with 2 others, you have to take the sum of those interactions. This is an interaction for this orbital that will be antibonding. It's going to go up. This will be an interaction for this orbital, which is bonding. It will go down. And the net result is no change at all. Here is the in-phase orbital that results from these mixing. This is the one that goes down. There's the out-of-phase orbital that results from these mixing. This one goes up. And let's figure out what happens here. Okay? This orbital interacts with this orbital to do what to that orbital? What happens to the energy? Goes up, right? Because it's the upper of the two orbitals. So this one's going to go up. And I've drawn these out of phase so that you'll be convinced this goes up. When this and this interact, this one goes down. I've drawn them in phase to represent the fact that they will interact in phase to stabilize this one. And so we can figure out what the resulting orbital looks like by summing this and this and this. And you can see what's going to happen is that at this end, the hydrogens are going to add. At this end, in the middle, the hydrogens are going to cancel. And the resulting orbital is going to look like that. Okay? So this is what I hope that, at least you will, if not be able to do at the end of the lecture, at least be able to sit and witness other people doing with some knowledge of mixing orbitals to figure out molecular orbitals for a larger molecule. So all we've done really is figure out what the orbitals are for linear H3, the transition state for hydrogen exchange, by starting with an H and an H2 and doing orbital mixing. So there are the actual orbitals. Here's where the electrons are for H3 dot, the new geometry. And if this is a transition state, then it must be the case that there is a distortion which leads to lower energy, and it is in fact a distortion that ejects one of the atoms and makes an H2 molecule. And it seems like maybe we should be able to predict that as well, that this would be a favorable distortion. How would we do that? Well, we can think about interactions between orbitals that have different energy. We've already done that in sort of this direction, but supposing we start now with linear H3 and we ask, how might these orbitals interact? Well, at the moment they won't interact because this has symmetry different from this. But supposing that we pull this hydrogen away and we push this hydrogen in, I think you can see if we're pulling this hydrogen away and we try and mix these orbitals, then the interaction between this hydrogen and that center hydrogen decrease. If we're pushing this one in, the interaction between this hydrogen and that hydrogen increase. And as a result, this distortion, which allows the mixing of orbitals which at the high symmetry geometry have different symmetry, actually is stabilizing and takes us back to H dot plus H2. Okay? And the moral of the story is that mixing between filled and empty orbitals of different symmetry can favor a molecular distortion that allows these orbitals to mix. Okay? And we'll come back to that shortly, too. Okay? So orbital mixing, if it lowers the total energy, is a good thing. And even if we have high symmetry, sometimes it's very good to allow the orbitals to mix by breaking the symmetry. And, of course, the closer the orbitals are that are mixed by breaking the symmetry, the stronger their interaction will be. Let's make an AH2 molecule. We're really moving on now. We've gone from H2 to H3. Now we're actually going to put p orbitals on our center atom and call it an A atom. Okay? So here is an A atom, some atom from the first row of the periodic table. Okay? And here's this 2s orbital. I even drew it like a 2s orbital. There's a little node, radial node here if you look hard. And here are the 3 degenerate p orbitals. And you already know that if you have 2 hydrogens, there are 2 possible combinations. There's an in-phase combination and an out-of-phase combination. And so all we're going to do is see which orbitals of the A interact with which orbitals of the H combinations. And that's what we're going to do for the rest of the morning, actually, when we get to transition metals as well. We're just going to construct symmetry combinations of hydrogens or ligands and see what orbitals they interact with on the central atom, either atom from the first row in this case or a transition metal when we get to there a little bit later on. So here's the symmetrical orbital. Clearly it interacts with 2s. Right? You see they have the right symmetry to interact. Imagine 2s sitting in between here. There's an in-phase combination. And there's an out-of-phase combination. This one goes down. This one goes up by about the same amount, a little bit more, actually. What will interact with the out-of-phase combination of the hydrogens? Which of these orbitals? Px, that's right. So this orbital is perfectly set up to interact with that set of hydrogens. One combination goes down. One combination goes up. How about this p orbital that is in the y direction, or this one that's coming out at us that's in the z direction? Will they interact? No, because these hydrogens lie in the nodal plane, and once again, you can go through, if there's a bonding interaction, it's canceled by an anti-bonding interaction. The main thing to say is they have different symmetry. These are symmetrical to the plane of the paper. This one's anti-symmetrical with respect to the plane of the paper. Here, this one's anti-symmetrical with respect to the x-axis. These are symmetrical with respect to the x. So there is no interaction. So these two orbitals come across unchanged. And here are what the actual orbitals look like. Let's think about having a linear AH2 molecule and deciding whether or not it's going to stay linear. As you know, not all AH2 molecules are linear. I give you water as a good example. So let's see which ones are predicted to be linear, which ones aren't, and maybe we can even say something about how bent various molecules are. So, for instance, you might think that water and H2S would be equally bent. Not. Bond angle in water is about 104 degrees. Bond angle in H2S is about 90 degrees. So maybe we can use our theory to predict something about the size of bond angles. So let's imagine that we're going to bend a linear AH2 molecule and see whether, in fact, that's a good thing to do for different numbers of electrons. Okay? It turns out that it is easiest to analyze the situation in two stages. Stage one is, let's look at the energy of each of the orbitals, imagine we bend, and see what happens to the energy of that orbital. It's called first-order perturbation theory. Next thing we're going to do is we're going to allow the orbitals, if they acquire the same symmetry, to mix. It's called second-order perturbation theory. Okay? So let's begin with first-order perturbation theory. It's really easy. Imagine those two H's get close to each other. Is that a good thing in terms of bonding? Yeah. So to the extent that this molecule bends, this orbital should go down in energy. Okay? How about this one? Is it good for those hydrogens to get close to each other? No. There's something else that's bad about this. Anyone see what's going to happen if you move those hydrogens off the axis of that p orbital? You're going to lose bonding, right? P orbitals are highly directional. In fact, you could imagine bending this so that both hydrogens were there in the nodal plane of the p orbital. There'd be no interaction at all. So there are two reasons why that orbital is going to go up. One is that to the extent that there is HH interaction, that's bad. But probably even more important, we're losing bonding by moving those hydrogens off the axis of the p orbital. And so I'm drawing this as going up more than this one goes down. Do you see any hydrogens here? No, so those don't really care what the hydrogens do to first order, because the hydrogens aren't there in those orbitals. Right? So those are going to come across unchanged. How about this orbital? Well, once again, hydrogens are in phase, should go down. Why don't we worry, by the way, about what happens in terms of the overlap of those hydrogens with this 2s orbital? We worried about it with 2p. Why don't we worry about it with 2s? Yeah, it's spherically symmetrical. It doesn't care. There is no directionality to an s orbital. Okay. So once again, we would guess that this orbital is probably going to go down a little bit. And this one is kind of hard to guess whether it's going to go up or go down, because it would go up from moving these hydrogens closer together, but it would go down because here we have an antibonding orbital, and to the extent we move those hydrogens off the axis of the p orbital, that should stabilize it. As it turns out, it doesn't matter what it does, because if you look, Here we have a bonding orbital. Here we have a bonding orbital. Here we have non-bonding orbitals. Here we have an anti-bonding. Here we have an anti-bonding. By the time we filled all those orbitals up, the molecule would fall apart. So we don't really care what this one does. I've forgotten what. I think I made it go down. I guess I decided that moving it off the axis of the p orbital was good for it. And that's called first-order perturbation theory, looking at the original wave functions and seeing what they do and how they change on some sort of perturbation like a geometrical distortion. So now we need to worry about second-order perturbations and what might mix with what. Okay? Is this 1d2 orbital going to mix with, say, this p orbital? No, because this has a node and this doesn't have a node. But this orbital could certainly mix with the p orbital, right? It's in phase here, symmetric, so these guys could mix. This could also mix with a p orbital. This is now the plane p orbital, so if we're bending in plane, this doesn't mix. So we actually have two interactions to worry about. We have to worry about the interaction of this orbital with the p orbital and the interaction between this orbital and the p orbital. Which one will be more important? Yeah, that's right. This is going to be more important because this orbital is way, way down in energy. Why is it way down in energy? Well, if we took the average of these two, we'd say that's going to be about the average of an s orbital, and the average of an s orbital is well below a p orbital. Right? So this is much farther away from the energy of the p orbital than this antibonding one is. Right? So this is a good example of the fact that the interactions that matter the most are those that occur between orbitals that are close in energy. Right? So we would certainly predict that the major effect of orbital mixing is going to be this with this. And what will that do? Well, the lower orbital will go down, and the upper orbital will go up. And I think we now get to see what the actual orbitals look like. And you can see there really is some, interaction between those hydrogens. Now, let's start putting electrons in and see what we predict for geometry. So here we go. Put 2 electrons in, and we have lithium dihydride. I'm guessing lithium dihydride may not exist, but sorry, it's actually lithium dihydride plus. The plus seems to have gotten left off. It might not exist because I think if you take lithium hydride and add proton to it, you probably get H2 and lithium ion. But, we theoreticians don't worry about things like that. Supposing that, in fact, we somehow made it, would it be linear or bent? It would be bent. That's right, because we're putting 2 electrons into an orbital that's going down in energy. So here we have 4 electrons. We're now at beryllium hydride. What's the geometry of beryllium hydride, would you guess? It would be linear, right? Because this went down a little bit. Went down a little bit because there's bonding interactions between the hydrogens, whereas this went up a lot. It went up a lot because not only is there antibonding between the hydrogens, but also we moved the hydrogens off the axis of the p orbital. So that's why this one went up. Since this goes up more than this goes down, the net result is we predict that beryllium dihydride should be linear, and indeed it is. So now we have BH2. And I will tell you the truth, you cannot predict unequivocally what the geometry is of BH2 from a diagram like this. The reason is that we don't really know how far down this goes on bending and whether it will overcome however much this goes up. I mean, Tom Kandari would have to do a calculation for us to be able to predict. As it turns out, let's just take the empirical fact that indeed BH2 is bent. The bond angle is something like 135 degrees. Okay? So let's just remember that. 135 degrees for BH2. Supposing we add another electron. Now we have triplet CH2. That is the ground state of CH2. Now, there was a huge, huge dispute about what the geometry was of triplet CH2. I think it's sort of like R.B. Woodward of spectroscopists, Canadian, and this is old age, I'm sorry, I'm having a senior moment. Hertzberg did an experiment in which he actually measured, using UV spectroscopy, he measured the bond angles in CH2 in its singlet state, and he got that right. As we'll see, it's a small number. He got data for triplet CH2, and he said, gee, this doesn't make any sense. Either it's linear, and there's some funny bands missing, or it's bent, and there's some other funny bands missing, and I can't really tell the difference, so I will guess that probably it's linear. Well, this would be like R.B. Woodward guessing the structure of a natural product. When everyone said, well, he guessed it, so that must be right. So after that, everybody in the world believed that CH2 was linear, even though Hertzberg said he really didn't know and he was just guessing. Okay. Theoreticians. John Popel won the Nobel Prize. He developed a semi-empirical theory, got CH2 bent 135 degrees. He apologized for getting it wrong. Susanna mentioned H.C. Longet-Higgins. H.C. Longet-Higgins did not believe in ab initio calculations. There was a man in his laboratory named Frank Boys. H.C. Longet-Higgins was the professor. Frank Boys was the reader, lower level rank. Longet-Higgins was this loud, flamboyant, wonderful man. Frank Boys looked like a bookkeeper. He wore a derby, three-piece suit. Christopher gave Frank Boys a horrible time. Frank Boys' very first ab initio calculation to really tackle a molecule of any size did triplet CH2, got a 140-degree bond angle. Christopher wrote this paper, scathing paper, 2 years later, saying, well, someday these machine calculations may be worth something when they get CH2 right. You all know what the bond angle in CH2 is, triplet CH2, because how does that orbital respond to bending? Does it care whether it's linear? No. So if BH2 has a bond angle of 135 degrees, you all know, without doing any calculations, that triplet CH2, right? So you could have saved this huge controversy. And no one did. The bond angle in BH2 was known, and no one thought, gee, CH2, triplet CH2 is going to have the same bond angle. Okay, so if BH2 is bent by 135 degrees and CH2, triplet CH2 is bent by about the same amount, how about singlet CH2? What do you predict it's going to be? More or less bent? More bent, because we're now putting 2 electrons in an orbital that's going down in energy. And indeed, you're right. The bond angle in singlet CH2 is about 104 degrees. Let's add another electron. Now we have nitrogen, NH2. You all know what the bond angle must be. 104 degrees, right? Because we put an electron in an orbital that doesn't care. What do you think the bond angle in water is? 104 degrees, yeah. See, it's easy. So why do you think H2S is more bent than water? Well, there are lots of reasons. You can say it's bigger atom, and so the H's don't get in each other's way as much. There are lots of hand-waving arguments one can use. What I like when you play this game is that you're forced to make a prediction. Maybe wrong, but at least you're forced to make a prediction, because what we would guess is that if water is, the H2S is going to be more bent than water, it must be that this orbital must go down further. Why does this orbital go down? Well, a little bit of it was the bending of the in-phase combination of hydrogens up here. But the main thing was mixing, right? And mixing depends on an energy difference, correct? So let's ask the question, is the energy difference between a p orbital and an orbital that has lots of s character bigger for sulfur than for oxygen? And now I teach you something about, you probably all know this, but I'll pretend I'm teaching it to you to make myself feel good. Turns out that we all think that S and P orbitals have the same size, because we all live in the first row of the periodic, well, you guys don't, but I live in the first row of the periodic table, where S and P orbitals do have the same size. That's an accident. They don't have the same size anywhere else in the periodic table. S orbitals are much more compact than p orbitals. It comes right out of the Schrödinger equation. Right? All you have to do is look up solutions to the Schrödinger equation. You'll convince yourself that s orbitals are much more compact. So consequently, since p orbitals are more diffuse, when you make a bond, you're going to make a bond using mostly the p orbital, and you're going to leave the s orbital kind of out of the game. Consequently, this orbital, which is antibonding, there isn't really very much overlap between the hydrogens and the s orbital because the s orbital is quite contracted, quite small, compared to those distances in H2S. Consequently, if this is less antibonding in H2S than it is in H2O, this gap is going to be smaller in H2S, and indeed you would predict then smaller gap, more bent molecule. And indeed, that's what happens. Tell me about SiH2. Tell me about carbene, SiH2, but with silicon in place of carbon. What do you think is going to happen for SiH2? First thing to remember is that we don't care about the number of electrons here, right? Because for those electrons are not there when we're at carbon. So forget about those. They don't matter anyway in terms of bending. So the question, I guess, is, will that orbital go down further in energy when we have silicon than when we have carbon? What do you think? Yes, it will, for the same reason that it did in H2S. This is not as antibonding an orbital because this s orbital is pretty compact. It doesn't overlap with the hydrogens very much. Consequently, this gap is very small. If Tom Kundari does a calculation, that's what he finds in the linear geometry, that really is a rather small gap. And consequently, you get a lot more out of bending SiH2 than you do out of CH2. And the result, not only does singlet SiH2 have a bond angle of about, what would you guess? 90 degrees. But also, it's the ground state. It's so stabilized that there's so much stabilization doing this that it does not pay to take an electron out and put it in this orbital with parallel spin, because when you have parallel spin, of course, you minimize the Coulombic repulsion. Okay. Oh, one last thing, a molecule that doesn't exist, but we can predict its geometry. How about neon dihydride? By the way, please note that we still have bonding, right? We have not filled up this antibonding level in neon dihydride. So we still have bonding. Even though it has 10 electrons, we still have bonding. It's an interesting kind of bonding because what's causing this to hang together is we have filled up this antibonding orbital, which killed off all the bonding here. The only thing that's holding this molecule together, is this p orbital donating a pair of electrons to the outer phase combination of hydrogens. What do you call a bond made with a lone pair donating into an empty orbital? Dative bond, yeah. This is a dative bond. It's a funny kind of dative bond because, if you'd like, the empty orbital is on two different atoms. Right? But it is a dative bond, and that's what holds this together. This is called 3-center 4-electron bonding. And so the molecule, at least in principle, might hang together. And if it did hang together, what would its geometry be? Well, whatever stabilization we got out of this mixing, we're now losing when we put electrons up here. And so you would predict that NEH2 would be linear. Okay, we don't know what NEH2 is, but we do know what xenon difluoride is, linear molecule. And again, it hangs together, and it hangs together for a very good reason. If you have a dative bond, you want something in the middle that's a pretty good electron donor. That's xenon. It's much better than neon, that's for sure. And at the ends, you want something that's pretty good acceptor. That's fluorine, a lot better than hydrogen. So you can see why it is that xenon difluoride not only might exist, but if it did exist, and it does, would be linear, and it is. You might ask, what happened to bonds? I mean, here we have these orbitals. What happened to bonds? We'd like to think that in an AH2 molecule there might be bonds instead of orbitals. Well, there are. If you take the sum of these two orbitals, you're sort of breaking the symmetry. But still, you wind up with something that looks like a p orbital on A directed toward one of the hydrogens with nothing on the other hydrogen. If you take the difference, you wind up with the same thing in the opposite direction. And these are perfectly fine orbitals to use. It turns out you can prove very easily that when you mix two filled orbitals, you don't change anything. You can take sums and differences. It makes no difference at all. It has to do with the properties of determinants. The problem with these orbitals is, they're useful for visualizing, that there really is a bond here and a bond here. The problem is that if you wanted to measure a photoelectron spectrum, this set of orbitals is not a very good one to use. Okay? Because when you take an electron out, now suddenly the interaction between those orbitals becomes very important. Much easier to see it here, where you would say, how many bands would you see in a photoelectron spectrum of this AH2 molecule? See two, right? One from here, one from here. Whereas here, it's kind of hard to see that you'd see more than one. You would, because there's interaction between those two. In fact, when you account for that interaction, you get back to that picture. Nevertheless, for nice closed shell molecules, you can add and subtract orbitals and get localized bonds if you have a mind to. Okay, so what I've done here is I've simply shown the seven actually combinations of ligands that you can have if you have 6 ligands. Okay? So there's this one that looks like an s orbital. There are these 3 that look like they're going to interact with p orbitals. And then what's a little confusing is there are 3 more that look like they can interact with d orbitals. And maybe you all know this, but that is obviously impossible because there are only 5 d orbitals. So the problem is that these 3 are not linearly independent. So for instance, if you take this one and subtract this one, so turn this red into a blue and turn this blue into a red, you wind up with this one. So this and this are really the same as that. You can find another combination, though, if you take the sum of these, and you can see then the reds get big, and around the girdle here, the blues will sort of add. And that, of course, is what gives you something that looks like dz squared. Okay. I did this simply because it's puzzling sometimes to people why dz squared doesn't look the same as dx squared minus y squared. And the answer is that they are degenerate orbitals and that any linear combination of them is perfectly acceptable, and you can never get them to look exactly the same. And this is a problem anytime you have a 3-fold axis of symmetry. Okay, you see it all the time. If you remember the orbitals for the 3-membered ring made of hydrogen, they look very different. Does anyone know that an octahedron has a 3-fold axis of symmetry? It goes through the faces, yeah. So that's why you see this weirdness. And so, it's totally arbitrary what orbitals you take. And in fact, Tom can probably tell you that in some cases, because the computer doesn't know that z squared is supposed to be the unique axis, you wind up with things that do not look like dc squared orbitals or dx squared minus y squared orbitals. You wind up with some weird linear combination that doesn't look like anything. And they're perfectly acceptable orbitals. So here is Joe Feng is now taking over from Dave Rovat. Here are actually those combinations. And here's what happens when they interact with a metal ion. Now, I should tell you how stupid I was. I wanted to show you really simple pictures. So I said, Joe Feng, could you make pictures with metal ions interacting with hydrides? Because then there'll only be hydrogens. But it turns out that something bad happens when you get far enough along toward the left side of the periodic table. Because you have huge, very high oxidation states of these metals. What happens is that the d orbitals, which are supposed to be above the bonding orbitals, fall below them. Right? So what Joe Feng very cleverly did was he did his calculations on things that had less than the full complement of 18 electrons. And so what we'll do is we'll just pretend that those are really calculations on 18 electron atoms. And we'll pretend that what we're going to do is we're going to take the 6 protons from the zinc nucleus, put them in the hydrogen, so instead of having H minuses, we have neutral ligands, and we'll say that that's sort of a model for what chromium with 6 ligands might look like, and that's just what the orbitals are. And I think that they probably look pretty familiar too. I'm going to go through them real fast. Here is dx squared minus y squared interacting with the hydrogens, dz squared interacting in a bonding way with the hydrogens, the s orbitals, the p orbitals, and then we have these 3 non-bonding d orbitals. They do not have the correct symmetry to interact with any of the hydrogen combinations. And then we have the anti-bonding combinations of the hydrogens and the metal d orbitals. And those are the ones that, of course, you do not want to put electrons into. But we will in a second. Okay. I thought it might be fun for you guys to see what happens when you have a carbonyl group. You all know what happens when you have a carbonyl group. You wind up getting back bonding, and let me just point out where that occurs. You can see that there is stabilization of these 2 orbitals relative to this one, which is supposed to be dx squared minus y squared, because these orbitals can interact with the carbonyl group. And in fact, you might wonder, are these really interacting with the carbonyl group? It looks like they're just interacting with the oxygen because there's hardly any contribution from that carbon. Hard to see maybe, but can you sort of see that all of this is on oxygen, very little on the carbon? And there's a good reason for that, because when this d orbital mixes, it mixes not only with the pi star orbital, which is what you guys all think about, but it also mixes with the pi orbital. It is true that this is what provides stabilization, because when filled orbitals mix, it doesn't do anything. Doesn't help at all. But filled and unfilled does provide stabilization. However, if you want to see what the actual orbital looks like, you have to include all of this mixing. This mixing, this is lower than this orbital, so it mixes with this phase. This is higher, so it mixes in phase. And when you add all these things up, you can see that on the carbon, you get cancellation. On the oxygen, you get addition. And that's why this orbital looks the way it does, okay? Because this d orbital really is mixing with both pi and pi star. This just shows what happens if you have an electron donor. Joe Feng did calculations with chlorine. And again, it's a model. And again, it's interesting to see what happens. Chlorine, which is lower in energy than the d orbital for the there's one interaction which is down here that's bonding. There's another up here which is actually anti-bonding for the d orbital. It's interesting that there's a little bit of, what's it called, a delta bond? What do you call it when you, Tom? Yeah, delta bond. Yeah, there's a little bit of delta bond interaction because you can actually see a little bit of that orbital mixed in because it does actually overlap with the chlorine orbitals. And actually, you see it in this combination where the chlorine sort of cancels out. And you can see that chlorine actually destabilizes both of these orbitals because here again is dx squared minus y squared, and these orbitals get pushed up by interacting with the lone pair on the chlorine. So I thought for fun we'd just see what happens when you have 20 electrons. Okay, so we're going to put 2 more electrons into something that already has 18. Let's put them into dz squared. What do you think is going to happen? Well, clearly this is an antibonding orbital, and clearly what's going to happen is that this is going to try and relieve some of the antibondingness by moving those 2 hydrogens away. So this is the kind of distortion that one expects. It's, again, a sort of Jahn-Teller distortion because these are degenerate orbitals. And what happens is one pair of hydrogens, that pair goes off. When that pair goes off, what was a bonding orbital down here goes up in energy. What was a p orbital that was bonding to that pair of hydrogens, there it is. That disappears because the hydrogens are going away. And one of these p orbitals that was part of this comes down in energy. And if you actually look at these MOs, you see just about the pattern that I told you. Again, this is a calculation that Joe Feng did because we didn't want to have 2 electrons there and have something that would be so electronegative that all the d orbitals would be down below the bonding orbitals. But I just want to show it to you for a moment. It doesn't have 16 electrons. It only has 14 because the last CENTC meeting we had on the web access, somebody pointed out, Karen pointed out, and I think Susanna said, yeah, really if you have a nickel, well, they said actually platinum 4, but this would be nickel plus 4. You'd wind up with 2 extra ligands adding to make an octahedron, and you can see why. Because if you have 14 electrons in a square planar, then this is an empty orbital, this is an empty orbital, you've got 2 empty orbitals, and so it's easy to add an in-phase combination of ligand pairs and an out-of-phase combination of ligand pairs. So, very easy to explain. I just thought I would show you how clever S and dz squared orbitals are. They have the same symmetry now when you have no longer axial ligands. And for the equatorial ligands, you would think the lowest orbital would want to increase the coefficients in the equatorial plane, and it does that by mixing dz squared in exactly this way with the s orbital. And then, of course, there's an anti-bonding combination in which these mix out of phase, and now you mostly have the dz squared orbital because these cancel. And I just thought that was really clever when I saw it. So I thought I would share it with you. After a while, you get fascinated by these things. You say, that's pretty neat the way the molecule does that. Another way you can do the distortion is to put the 2 electrons in x squared minus y squared. Now you have 4 ligands in the equatorial plane that are antibonding, so that they are going to tend to move away. And what that does is get rid of that, and that, and that. And you really don't want to know. Okay. What you do want to know is that these are the filled MOs of nickel dihydride. That would be what you'd get if you lost all of those ligands from the molecule that we had a moment ago. You see that there's a low-lying non-bonding orbital, and so really to get something that's going to be stable, you need to put 2 electrons there, and that's sort of our model for NiL2. And this just shows, again, this s orbital mixing with the dz squared. Now, because we have 2 axial ligands, the mixing goes in the opposite direction. The s orbital wants to make that a big coefficient, or a big contributor, and the non-bonding combination has these mixing in the opposite way to put more density in the equatorial rather than the axial. Metal H5, here are the symmetry combinations, and I'm just going to pause for a second to show you that one gets these complicated looking orbitals because, again, we have a 3-fold axis of symmetry. So what happens is that here are orbitals that are combinations of p orbitals and d orbitals, and you can see they look totally different, even though they're degenerate. Same thing up here. And so this would be the MOs of FeL5. And this just shows how the orbitals mix up with the p's and the d's mixing. And you can see the orbitals down here are mostly d. The orbitals up here look much more like p orbitals. So here the contribution is mostly from the d's. Up here it's mostly from the p's. So now let's talk about something that's kind of interesting because it actually is not just looking at orbitals. Let's talk about what happens if you have an AH5 complex and you have 2 axial ligands that have different electronegativities. Clearly, if they have the same electronegativity, those 2 orbitals have different symmetry. They won't mix. This is a bonding orbital. It's a bonding p orbital. This is the dz squared orbital in an anti-bonding fashion. We should really include the dz squared orbital that bonds to those H's, but we really don't have to worry about interactions between filled orbitals if you want to just know what the energetic consequences are. If you want to see what the orbital looks like, the end orbitals, you do have to worry about it. But since filled orbitals interacting with filled orbitals do not give you any stabilization, it's only filled with unfilled. That's why I've just drawn those two for simplicity. Okay? And there's no interaction because of the difference in symmetry. This has a symmetry. This is antisymmetric. This is symmetric. So where you would get a difference is if you had an A and a B here, where A and B have different electronegativity. For the sake of argument, supposing that A is more electronegative than B. That is, electrons on A have lower energy than electrons sitting on B. The name of the game then is to mix these orbitals so that the coefficient on A, the density on A, increases. And you can do that by mixing up these two orbitals, which had symmetry but now have lost symmetry because we've changed these atoms so that they're no longer symmetric. And let's just see what happens if we do the mixing so that we increase the coefficient on A. Okay? So I've drawn the phase properly so that when I mix these two, this is going to go down because we're increasing the coefficient on A. Now let's look what happens to the rest of the orbital because that's what's important. What's going to happen is that B is going to get much smaller. And that makes sense, right? Because if we're going to put most of the density on A, then it's going to be at the expense of B. But what's interesting, what's really interesting, is what happens to the rest of the orbital. This mixes in to kind of cancel some of this red color. So you wind up with a small contribution here, and you wind up adding here. So you wind up with a hybrid pointing away from A toward B. Right? Does that make sense to everyone? Can you see that that's what we've done? So essentially, if we have a very electronegative atom here, we're going to wind up strengthening the bond to B. This is just to show what happens with the anti-bonding orbital. So bonding to the less electronegative atom, that's the one that's going to release more electrons toward the metal, is strengthened, and bonding to the more electronegative atom is weakened by this kind of interaction. So let's see a puzzle and see if maybe this explains it. So Jim Mayer and I and Ahmed Ahmed did some experiments. We did some calculations on this reaction. It's also, we've done calculations and Jim's done an experiment with the same reaction with silanes, and we've started some work with hydrocarbons. Let's just talk about this because it's easy because we're adding just H2. And what's interesting is that if you add a Lewis base, in this case I'm using hydroxide to illustrate, it turns out you get a rapid acceleration of this reaction, huge acceleration. And calculations actually tell you something interesting, and that is that the acceleration has a thermodynamic origin, that this delta H2 is much larger than delta H1. This becomes a much more exothermic reaction, and that's why it's much faster. Why does it become more exothermic? Well, you have a thermocycle here. And one way of looking at it is that it becomes more exothermic because this apparently, the product apparently binds OH minus much more tightly than the reactant does. Because this is a thermocycle, you can either say that this is a more exothermic reaction than this, or you can say this binds more tightly than that. There are two equivalent statements. What makes this a more exothermic reaction is that the binding here increases. Why does the binding increase? Well, here is an electron-releasing substituent. We said that electron-releasing substituents tend to direct bonds toward themselves, leaving the more electronegative substituent with a weak bond. What's going on here? Which is a better donor, O2 minus, O minus 2 rather, or OH? I would say O minus 2. In fact, I know that because I've seen lots of systems where this bond is always very long next to across from an oxygen. It's exactly what we said before. When you have something that's very electron releasing, it weakens this bond. Here, in fact, the bonds have to be of equal strength, right? Because they're the same bond. They're both OH bonds. So we've gone from a very weak bond to a very strong bond. That's exactly what we expected from the orbital interactions. That's exactly what the thermodynamics are telling us, that this bond must strengthen. That's why the reaction is accelerated. Okay? So that solves an interesting puzzle. I mean, you wouldn't really think that adding something to osmium would make it hydrogenate easier. You know, doing one addition facilitates another addition. But it does, Ahmed's experiments and our calculations say that is true. And it does because this ligand gets bound more tightly when this becomes less electron releasing on adding an H. Okay. I want to talk for the rest of the hour about AH2, bent AH2 in particular. And I want to point out that sometimes there are really bad ways of doing things. You can always generate molecular orbitals any way you want. You might think that if you want to do bent ML2, you might just want to do the same thing we did for AH2 and just bend and see what the orbitals do. Problem is we have too many orbitals of the same symmetry. So there are 1, 2, 3, 4, 5 orbitals that have the same symmetry, and you have to mix them all up. And there are 3 orbitals that have a different symmetry, and you have to mix them all up, and it's a mess. And so you really don't want to do business this way. I discovered the hard way, because I was going to present this to you this way, and I started, and I thought, no, that's a big mistake. Okay, so here are what the actual orbitals look like for zinc dihydride, which if you move the protons out of the zinc onto the hydrogens is the same as nickel L2. And what you see is that the highest occupied orbital is an interesting orbital. It is something that is a d orbital, but it is hybridized in that direction away from where the hydrogens are. And then there is an empty orbital, which is basically a p orbital, but it is also hybridized away from where the hydrogens are. Okay? And this just shows you where all the orbitals wound up. You can actually construct this orbital very easily by saying, well, what could I do to interact with a pair of hydrogens with a zinc s orbital and a zinc p orbital, and you can construct the bonding combination, and here we have the d orbital combination, and so on. We're going to do things a little bit differently. I suggested that you should all read, and I'm sure no one did, the Hoffman paper, the Nobel laureate address on isolobal approach to finding frontier orbitals. Let's just go through it and see how that works, because that's an easy way of getting the orbitals. Okay. I'm not sure it has any scientific content, by the way, but it's an easy way of finding orbitals. So what we're going to do is we're going to remove 2 ligand orbitals, 2 ligands and their electrons. Okay, and so that leaves us with this, but you can see that that is not really satisfactory because we have 2 orbitals, and when you ever have orbitals, you have to take sums and differences. They will interfere either in phase or out of phase, and so that's all I've done here, is I've taken sums and differences of those orbitals. What's complicated now is that I want to make NIL2, not NIL2 plus 2. So I need to add 2 electrons, and this is where the Hoffman analysis is, I wouldn't say dangerous, I'd just say you have to pay attention. You have to remember that this looks like what kind of orbital? D, yeah? It's a d orbital that's hybridized in that direction. Whereas this looks a lot like a p orbital. Which is lower in a transition metal, D or P? D. Okay, so unlike the case in a carbene, where everyone would say, yeah, that's the lower energy orbital, that's the higher energy orbital, it's different in transition metals because Ds are lower than S's and P's. So this is actually where the electrons go. This is left empty. And that's exactly what we saw on the previous slide. Okay? By the way, let me just convince you that, in fact, that is a p orbital or a hybridized p orbital. If I just take the sum of these, the vector sum, I get this. Okay, so an ML2 fragment will have a filled orbital that looks like that and an empty orbital that looks like that. And so this is something probably you've all seen. This would be a bent NIL2 interacting with an alkene. Okay, and you can see that this has the right symmetry to interact with the pi star. This has the right symmetry to interact with the pi orbital. There is the interaction for the pi interacting with this empty orbital. This gets stabilized. And if that was all that happened, you would say that there is a dative bond formed between these carbons and the nickel. And there are, in fact, molecules that look like that. However, there are also molecules, we call that a pi complex, there are also molecules which differ from this by having strong interactions between this filled orbital and this empty orbital, which provides us with another, if you'd like, bond. And then you have a metallocyclopropane. This is the Dewar-Chatt-Duncanson model. I think probably all of you have seen this. But let's see if we can explore it a little bit further. This is just saying that really a more interesting case would be if we had platinum here because, oh, I know. So what I want to do is I want to decide what would be the best orientation for a metallocyclopropane. Would we want to have the ligand orbitals in the same plane as these carbons? That, of course, isn't what happens in cyclopropane. In cyclopropane, the atoms that are coordinated to this are out of the plane. This, by the way, just shows that with these in the plane, there is a d orbital here that doesn't interact, right? Because this is coming out of the plane. This ligand's out of the, this lobe's out of the plane. This is behind the plane. It's anti-symmetric with respect to the plane of the paper. These are symmetric, so there is no interaction here. This is the orbital that can interact strongly. Now what I've done is I've given this the actual geometry that cyclopropane has, where the atoms attached to the platinum are now out of the plane. And our job is going to be to decide which of those two geometries is more favorable. Is it going to be just like cyclopropane, which would be this geometry, or is it going to be the first geometry? Okay? And we can do the same kind of interaction diagram. Now, this is, of course, invariant because it's symmetrical with whether we rotate it or not. Now, this orbital doesn't interact, right? Because we've rotated our platinum diphosphine, and the phosphaces are out of the plane. These lobes are out of the plane. This one's coming out at us. This one's going away. So there's a node here. This is not interacting with this orbital at all. The orbital that's interacting is this one. And so, of course, it goes down when it interacts with pi star. So which of these two is better? Which of these two geometries? And this is the kind of thing that I like because you can predict this without doing any calculations, just by looking at the diagrams. So from this, supposing we get this much stabilization, how much stabilization did we get from the other geometry where the phosphines were in the plane? We got that much, which is actually more than that much. Why is it more, and how do I know that it's more? How do I know that this is, in fact, a better geometry? Well, this is a pure d orbital. When it was allowed to interact here, it's a pure d orbital. It is lower in energy than this because this has an antibonding interaction between the phosphines and the platinum. So that pushes this up. What will that do to this gap? Makes it smaller. There's one other thing that goes on. Look at this. It's hybridized toward the olefin, whereas this is not hybridized at all. So there are going to be two things that make this stabilization bigger than that stabilization. The first is the denominator, smaller gap. The second is the numerator. This is going to be a stronger interaction than this. Okay? So we can unequivocally predict that this is going to be the preferred geometry for a metallocyclopropane, and I think that's neat, because it is. The barrier is about 25 kilocalories per mole. Tom Kodari would have to do the calculation to tell us that, or he'd have to do the experiment. But you can see that you can make that prediction unequivocally. And I think that's really neat, when you can do something with just drawing orbitals and say, yeah, you know, it's got to be this way. I mentioned that Susanna, I still did experiments, like until a couple of years ago. I made all of those. I didn't make them. My graduate students made all of these alkenes. Okay? They're weird alkenes in that what we did was we put a carbon chain across here and chopped carbons out of it. This was actually a 15-step synthesis, which I thought was really great until I talked to a natural product chemist, and they said, oh, that's sort of what we do to make starting material. Anyway, what's interesting about this is that this is what the calculations say should happen to the energy of the HOMO as you parameterize these double bonds. You have to parameterize because with this carbon chain, you can't stretch all the way from here to here. The molecule has to kind of fold up like a clamshell. So it's kind of interesting that the HOMO goes up just a little bit. We've done photoelectron spectra on 2 of these, and indeed that's exactly what happens. The HOMO goes up by a little bit, but the LUMO comes down like a rock. Just amazing. And one can explain this. And you can appreciate the explanation really easily. So when you do this, when you parameterize those lobes, clearly you're decreasing the overlap. That's why it goes up. Why doesn't it go up a whole lot? Well, what happens is you're parameterizing, and so you're changing these p orbitals into sp hybrids. Orbitals that have s character are lower or higher in energy than orbitals that are pure p? Lower. So we have 2 effects that are going in opposite directions. Decreasing overlap goes up, more s character goes down. The result is not very much change. Whereas for this orbital, both effects work in the same direction. Because when we decrease overlap, we decrease the anti-bonding character. When we increase the s character, we lower the energy. And that's why the energy going down here changes by about 4.5 times as much as the energy going up. So if we were to coordinate these alkenes to a metal, you would think that the dominant interaction would be between the metal and that, because it's coming down. So rather than being a donor, these alkenes should be great acceptors. Let me just illustrate that. So here's a bent phosphine. That's supposed to be a platinum. Here is one of the members of this series. This is the n=3 member of the series. Here's the interaction diagram. Here's the n=3 series, member of the series. This is the interaction diagram. When we get to the n=1, those orbitals will be closer in energy, and what will happen? They will, of course, interact more strongly, and this orbital will come down much further. In other words, when we go across this series, we should get more and more back donation from the metal to the pi star orbital. We should be depleting the metal of electrons by going from across this series. So how would you find that out? Well, you can do calculations, but you guys are all experimentalists. You can take NMR spectra. Okay, and we published a paper on this. Dionysius Nicolaides did all this work, most of the synthesis and all of the spectroscopy and all the organometallic chemistry. And I think this is the only experimental paper I've ever published in organometallics. And we go through all of the coupling constants in great detail. Let's just look at the chemical shifts, because chemical shifts say something about where the electrons are. So you would think that if, in fact, we are transferring electrons from platinum to the carbons should become more shielded as we transfer electrons, and that is what's happening. If we transfer electrons from the platinum to the carbons, the platinum should become more de-shielded. That's what happens. And if phosphorus is pushing electrons into the metal and the metal is pushing electrons into the pi star orbital as we go across, you would think that the phosphoruses should be able to get rid of more electron density, and indeed they should also go upfield, and they do. And we could go through all the coupling constants, but that isn't what this talk is about. So, of course, I shouldn't say of course. When Karen first came and interviewed at UW, she gave a great talk on reductive elimination. And I said, Karen, interaction between a pi orbital and a metal is exactly the same as the interaction that you get in reductive elimination. And she said, no. And about 4 years ago, she said, well, actually, I think you were right, Wes. So here is the interaction, same interaction, but instead of a pi orbital and pi star orbital, we're having H2. And what you're seeing is that there are 2 interactions. One of them is pure donation. That is the interaction between this orbital and this one, pure donor. And so if that was all there was, we would have this kind of complex. And this kind of complex, of course, has now been isolated much more common were the dihydride complexes. And of course, you see the same thing with RH bonds, not just HH bonds. If it's an RH bond, it's either a weak complex or it's an agostic interaction, really the same thing, empty metal orbital. But to really go from a dihydrogen complex to a dihydride complex, you actually have to do an oxidative addition. And it's kind of weird that there's a barrier, because you sort of think that, why couldn't it just sort of slide over from here to here? It looks like there should be some sort of continuum, but there definitely is a barrier. So why is there a barrier? Here is a cartoon for a reductive elimination. And what you can see is in the reductive elimination, what we need to do is we need to push these two together. But we don't want to push these two together too soon, because if there's still electron density out on these two atoms, that's going to be antibonding. So we have to kind of leave these here and try and decrease the amount of antibonding between the metal and the ligand by moving the ligand into the nodal plane of this d orbital. And unfortunately, it's very hard to do this while the R groups are still there. You can't really get these moved off the lobes of the d orbital, antibonding toward these ligands, without starting to do this. And if you start to do this, then you start to get a lot of antibonding here. And that's where the barrier comes from. You can look at it in the other way. Instead of looking at the reductive elimination, you can look at the oxidative addition. If you want to make this good at donating electrons into this RR antibonding orbital, you have to start by moving the ligands before you get these two very close. And that's bad, because now you're creating antibonding interactions between the metal. So how can you get around this? How can you get a much lower barrier to reductive elimination or oxidative addition? The answer is lose a ligand. If you lose a ligand, then you can move one of these ligands off to infinity, and the other one can sit in the nodal plane of the d orbital. So now oxidative addition, reductive elimination, having lost the ligand, should be much more favorable. And this is what Karen taught me. Karen had all sorts of examples of 6-coordinate complexes that do reductive elimination only after first losing a ligand. For 4-coordinate, it turns out that actually the ligand stays on. You lose some bonding, obviously, if you lose a ligand. And at least for the cases that Karen told me about, the reaction occurs with the ligand stuck on. What counts is the loss of bonding versus the difficulty of doing this. And maybe it's not surprising in a 6-coordinate complex where things are much more crowded and these ligands have axial ligands that are interacting with them at a 90-degree angle, that it's much easier to lose the one ligand in the complexes that are 6-coordinate rather than the complexes that are 4-coordinate. So this is, I think, a nice example of how orbital analysis shows why it is that something otherwise puzzling, that you lose a ligand before you do a reductive elimination, makes perfect sense. And this was published with Karen and Kevin Bartlett, who did the calculations. Additional reading. Most of what I've said, actually, you will find in this book. It's a great book. These are 3 students of Roald Hoffmann who were obviously influenced by Roald. Roald was also a tremendous influence on me. He was my first teaching assistant when I was an undergraduate. I've stayed in touch with him through the years. And when I first started my career and there were no calculations that could be done that were worth anything, Tom, all one could do was draw these kinds of orbital pictures. And that's what Roald did with great flair and great success. And finally, thank you very much for your attention.